Today's topic is about antioxidant butylated hydroxytoluene and various important groups present in its chemical structure which are involved in its function and stability and mechanism of action of butylated hydroxytoluene as antioxidant, how it prevents the oxidation of lipids. Complete oxidation of lipids. I have taken the example of vitamin D to explain the oxidation of lipids. How BT radical itself is stable after performing antioxidant activity. I will explain its two reasons, that is steric, hindrance and resonance. Hello viewers, welcome to my channel. I am Mudassir Abbas. Our today's topic is about antioxidant. I have taken the example of butylated hydroxytoluene that is commonly used as antioxidant in pharmaceutical. Butylated hydroxytoluene contains some important functional groups in its structure. It is a hydroxyl group that is involved in antioxidant activity of butylated hydroxytoluene because it transfers its hydrogen atom, and these are large bulky groups attached to the tertiary carbocation. This group, after donating hydrogen atom, become a radical and it is prone to further attack by any species. But these two bulky groups shields this group. Before understanding the mechanism of oxidation of butylated hydroxytoluene, we should understand the mechanism of lipid peroxidation. Oxidation of vitamin D includes three steps, that is abstraction, oxidation and termination or recycle. Oxidation of lipids starts in such a way that hydroxy radicals, which are always present in air. Oxidation of vitamin D starts from the attack of hydroxy radical to the molecule of vitamin D. Hydroxy radicals are always present in air and they are formed at that time when ozone is attacked by UV light. UV light has sufficient energy to split ozone into oxygen molecule and oxygen atom, and this oxygen atom is again combined with the moisture present in air that form hydroxy radicals. This hydroxy radical, when attack vitamin D, then it causes the separation of this hydrogen atom from vitamin D. This phenomena is known as abstraction. After abstraction, when hydrogen atom is separated from vitamin D, then vitamin D is converted into vitamin D radical and it is prone to attack by oxygen. When oxygen molecule attack this vitamin D radical, then it converts this vitamin D radical into peroxyl radical. This peroxyl radical again attack on the healthy vitamin D molecule and make two molecules. Out of them, one is peroxide molecule, that is inactive form of vitamin D. It is inactive because it contains highly polar group and vitamin D is lipophilic in nature. Then attachment of this polar group will make vitamin D inactive. And second component, which is formed after reaction between peroxyl radical and healthy vitamin D molecule, is vitamin D radical. Because when this oxygen molecule will be separated and will be attached to the hydrogen atom, then it will form peroxide molecule, and on other hand this molecule will be converted to vitamin D radical. In this way it will form peroxide form of vitamin D that are inactive form, and on other hand it will again form vitamin D radical, and this cycle will be continued. Hydrogen atom will be separated by hydroxy radical from vitamin D, that will form vitamin D radical. Then oxygen atom will attack vitamin D radical to form peroxyl radical, and then peroxyl radical will again consume another healthy molecule of vitamin D to form peroxide form of vitamin D and another vitamin D radical, and this cycle will be continued. All of vitamin D is consumed. That is the reason that fast degradation of vitamin D occur in pharmaceutical product naturally. How butylated hydroxytoluene prevent the oxidation of vitamin D and other lipids? When vitamin D radical is formed, then butylated hydroxytoluene transferred hydrogen atom of its hydroxyl group to the vitamin D and converts vitamin D radical back to the vitamin D, due to which oxidation of vitamin D is further terminated. Hence, when vitamin D radical is attacked by butylated hydroxytoluene, then it will again form vitamin D and BHT radical. However, BHT radical is not like the vitamin D radical, because BHT radical is stable due to two reasons. Its one reason is that vitamin D radical has steric hindrance. It contains the bulky groups in which three methyl groups are attached to the tertiary carbon, which make a bulky group that shields the BHT radical, that shields the oxygen atom of the BHT radical that is prone to attack by any acid or other species. Another reason for the stability of BHT radical is resonance. Oxygen atom of BHT radical that has transferred its hydrogen atom to vitamin D has 7 valence shell electrons, and when resonance occurs in BHT radical, then one of the double bond of ring of BHT is transferred to the carbon oxygen bond, due to which valence shell of oxygen atom become full and one extra electron is delocalized, and hence resonance of BHT radical continues onward. And this process happens again and again, due to which for most of time valence shell of oxygen atom remains full, due to which possibility of attack of any species on the BHT radical is destroyed. Hence, BHT radical is stable due to two strong reasons. Here, one important thing should be kept in mind, that formation of vitamin D radical from vitamin D by attack of this hydroxy radical is accelerated by acid, because acids have property to transfer proton, and this proton is transferred to hydroxy radical very rapidly when pH is acidic. Hence, when healthcare professionals are manufacturing vitamin D, keep in mind that acidity is much more dangerous for the stability of vitamin D, because acidic pH quickly convert vitamin D into vitamin D radical due to quick transfer of this proton to the hydroxy radical.